Hi, class. Welcome to the next section, chapter 10.1. Today we're going to talk about arcling. Now, chapter 10 in general is all about further applications of integrals. So now that we have more methods for integration, we'll look at more applications for applying integrals. So uh, let's say we wanted to use an integral to find the length of a curve. First, we need to form the approximation. Okay, so just like everything when we're finding areas and volumes with integrals, we first start with an approximation, and then we kind of refine it and turn that into an integral. So if we have a curve f of x, right, and we want to approximate what the length of that curve is, we would use a whole bunch of straight lines, basically, right? So what we're going to do is we're going to take our function and we're going to divide it into n subintervals. We can find lines that connect each of those endpoints of our curve at those subintervals. So let's say this was my curve from, I don't know, let's say A to B. If I wanted to use only one line to approximate my curve, I would connect A and B with the line. Okay, it's not a very good approximation, but I can at least tell you the distance between these points, right? Obviously, it's a little bit more than that because there's a curve here. So what if I use 3 points instead, which will give me two lines? It's very obvious that this is a much better approximation to the length of this curve than just the one line is, right? So obviously what's better than 3 points? Well, let's break each of these in half instead, and we'll do 5 points. Okay, so 1, 2, 3, 4, 5. That is very, very close, at least visually, to the length of the curve, right? And obviously, the more points I use, the closer and closer my approximation becomes to the actual line, right? So instead of drawing the area under the curve, we're drawing an infinite number of points and the lengths of the lines between them. And as those distances between them, you just get your curve, right? So we're going to call our initial point P naught, our last point Pn, for n points that we're going to look at. Then in order to find the length of our line, which we'll call L for length, is going to be the limit as n goes to infinity of the sum starting from I to n, where we're looking at the distance. So this is not absolute value since these are points. It's not a value between them, it's a distance, right? Which is a value, positive value, but these two outer brackets, these absolute value signs means distance, okay? The length of each line is given by the distance between its two endpoints. So a quick comment on this, absolute value is distance. So if I talk about the absolute value between two numbers, I'm talking about the distance between those two numbers, right? This is just now distance in two dimensions instead of one, which is what we call the absolute value, right? So the distance between my 2 points that are next to each other, pi to pi minus 1, is the square root of um, the two function values being subtracted and squared and the two x values being subtracted and squared. So if you don't remember your function for distance, this is how we calculate distance, right? You can go back to my pre-calculus stuff and we talk about distance in there as well. But you're subtracting the y values and squaring it, and you're adding that to the difference in x values and squaring that. But here we're not using y values, we're using our function value, right? Y and a function value, they're both the same thing. It's our output, okay? So notice that the difference in output between a function or a point and the point before it is just the difference in output for my function at that x sub I, okay? The difference between x sub I and x sub I minus 1 is the difference in x. That's my delta x, so my change in height and my change in x. All right, so I'm squaring those things and adding them together, taking the square root in order to find the distance between 2 points. Remember that the mean value theorem states that there exists some value c in between the open interval from a to b such that the difference in values in my outputs over the distance values, the difference in values of my inputs is equal to the derivative at that point, right? So Again, if you go back to the earlier calculus one stuff, um, mean values theorem, all it basically says is that if I have a continuous curve from A to B, the derivative between of my function, somewhere between there, is equal in value to my function value at some point between this interval. So somewhere in between the start and end point of my interval, the derivative of my function is equal to the rate of change of the function. Okay. So I can make my substitutions that I just had here. The delta f of x over delta x is the same as the derivative of my function at that value c that exists somewhere between my interval. Okay. If I move this around, let's say I solve for delta f of x, then I just multiply both sides by delta x, right? F prime of c times delta x is the same as the change in f between those 2 points. Um, so obviously we're getting closer and closer to looking at this as an integral. So I can replace these values here, um, and it can write that the uh, distance between those 2 points can now be written or considered as the square root of f prime of some value between I and I minus 1. So I'll just call this the ith c, right? Times delta x squared plus delta x squared. Okay. So the nice thing about this is that I can now pull out a common term of delta x squared. Okay. So now I have f prime of ci. Again, ci is just some value in between this interval where the function value somewhere between here is the same as the derivative, okay? Or the derivative at that point is the same as the rate of change between the two endpoints. So I pull this out, I have this f prime of ci plus 1 squared delta x squared. Well, that's nice because this turns into just delta x, okay? And that's looking real good for me developing some sort of integral, right? So I always need just one delta x, not a squared or square root or anything like that. So the limit, my line length is the limit as those number of points goes to infinity. And we sum up the distances between each 2 points, substitute in my function value. And so I have the square root of 1 minus f prime of some ci squared times delta x. This turns into an integral. This turns into d of x. And then I just replace my function here with f prime of x, right? Because as n gets really, really, really small, these points turn into, there's no points anymore since they're infinitesimally thin lines, right? This is just x, right? Every x value between this interval. So that is the length. This is the formula for arc length, right? So the length of a curve is given by this integral. Sometimes we have to choose between looking at x or looking at y, depending on what my function looks like, okay? While using the arc length formula, we often can come across integrals that cannot be evaluated directly, and instead we'd have to use some numerical methods, which we just saw at the end of chapter 9. Okay, so it is very, I'm not gonna say very common, but it's common enough to run into some sort of arc length you want to calculate, and you can't. You just can't. It's not something that's possible, or it's too difficult to do by hand, or even through use of like Wolfram Alpha or something, you might have a runtime of forever. Or I mean, maybe you sit there for 20 minutes and you wait it out. Who knows, right? Um, but it's very likely that you'd have to use numerical methods instead in order to come up with an approximation that's close enough, right? So you could use the error formulas that we talked about when we talked about these numerical methods to make sure you're close enough, okay? Um, A variation of the arc length formula is used to find the arc or the length formula. Okay, so basically instead of bounding from A to B, I would bound from A to, let's say, T, right? Some other variable. So that when I plug in that variable and I do my calculations, I come up with a function at that point that I can then use to find the length of my function at any length I choose. Okay, that's really only good if I want to use this arc length on the same function over and over and over again, right? So maybe I'm interested in what happens at this point. How long is my function? How long is my curve? And then at some other point down the line, I need to know how long the curve is there as well. That's when using this form and finding an actual formula. So I would integrate this like normal, and I would evaluate at the bounds of t equals a and t equals x, so that my end result is a function. But again, if I'm not going to use this function over and over and over again, there's no real reason to do that. Okay, but there are times when it is. So let's do an example. Okay, let's consider the function f of x equals sine of x over the interval 0 to pi, including those bounds 0 and pi. Okay, the area under the curve, not the length of the curve, but under the curve, is easy to find. We've been doing this over and over and over again up until now, right? The integral of 0 to pi for sine of x dx is going to give us a negative cosine, right? We're working in the opposite direction of the derivatives, so we're going to change sign, and it's going to turn into cosine. We're going to evaluate from pi to 0, right? Cosine of pi is -1, and cosine of 0 is 1, right? So I'm going to get -1 minus 1, and then I have this negative out there, so I can just go ahead and distribute that through, and I get a positive 2. So the area under sine from 0 to pi is 2. However, if I want to find the arc length, the length of sine of x from 0 to pi, I have to use the first derivative of sine, which is cosine. I then have to square it, right, and add that to 1. So I have square root of 1 plus cosine squared. You might say, oh yeah, we can do that, but we can't, right? So this is almost sine squared, right? But I would need 1 minus cosine here. So there's nothing, I mean, I can try to work on it, try to use some trig subs and things like that, but you'll never be able to actually find this. Okay, maybe you can if you really work hard enough on it, but you're not going to be able to find this, okay? So you can really only do this with numerical methods, all right? And numerical methods gives us approximately 3.8202. Okay, that's just me using 4 decimal points of accuracy. But yeah, you would have to use, left and right hand sums, maybe average them for the trap rule. You could use the midpoints, the Simpsons rule, whatever, but you'd have to use some sort of numerical method here. So let's do another example. Okay, let's find the length along y equals 7x from 0 to x equals square root 2. So here, we didn't actually do an example. So let's start with a very easy example here, okay? I need the first derivative of my function, which is just 7. I'm going to square it, and I'm going to add it to 1, right? And I'm going from 0 to root 2. So this just becomes 1 plus 49, or square root 50. When I integrate this, it really just gains an x. And I evaluate from root 2 to 0. And as you see here, I kind of split this apart a little bit already, because 50 is the same as 25 times 2. So square root of 25 is 5. I'm left with the root 2, and that x that I gained is here. So just to clean it up a little bit. So if I throw in root 2, this becomes 5 times 2, which is 10, and then minus the 0. So my area here is just 10. Okay, or I'm sorry, the length of the curve is 10. But my curve is a straight line, right? Y equals 7x is a straight line, which is nice because if I want to check to see I'm doing things right, I can just do this algebraically, right? I know how to find the length of a line. I just find the distance between the 2 points from 0 and from root 2. When I plug in 0 to 7x, I get 0. When I plug in root 2 to 7x, I get 7 root 2. Then I just subtract the y values, okay, and square it, and then I subtract the x values and square it. So 7 root 2 minus 0 is just 7 root 2. I square that, I get 49.2. Root 2 minus 0 is just root 2, and when I square that, I get 2. So this turns into 49 times 2 plus 2. Or if I pull out this common 2 here, 49 plus 1 times 2, which is 100. Square root of 100 is 10, which is the same thing that I got. So that looks pretty good, right? I'm fairly confident that I got my answer right because I did it algebra with regular algebra, right? Obviously, we're not finding the length of a line most times, right? We're finding the length of some curve. So let's do another example. Let's say we want to find the length of something more complicated. X squared equals y minus fourth cubed from the point P15 to Q88. Okay, so there are two options for us. Okay, the way that it's set up right now, I can isolate X or I can isolate Y. And one of them may be much easier or much harder or the same than the other. Okay, so, but it would be nice to know what my choices are. So if I solve for X, I basically just have to square root both sides or multiply by 1/2 power for everything. And so then I get 1 minus fourth to the 3/2. Okay. If I take the derivative, because remember we have to take the first derivative, I get 3/2 times 1 minus fourth to the 1/2. Okay. If I square this now when I throw it in, my integral is from 5 to 8 because I'm now talking about y's, right? So I'm looking from 5 to 8 here of 1 plus 9 over 4, y minus 4, right? dy, that's the function that is inside here. Even though it is an x prime, my function has to do with y, so I'd be integrating y. So make sure you're using the right bounds here, okay? This would be an x of y function at this point. The other function is that I solve for y. So I take the cube root of both sides, and then I add this 4, okay? And then now when I differentiate y, I get 2/3 x to the negative 1/3. And then when I throw that into my formula and square it, right? 1 plus the derivative squared, so I'll get 1 plus this squared. I get 4 over 9, right? So 2/3. And then this turns into negative 2/3. So now I look at this. I look at option 1 and I look at option 2, right? I want to make sure I'm not looking just at the derivative because this derivative looks like it's easier than this derivative to deal with because I have a square root, but a bunch of stuff on the inside. Not a lot, but something, right? Here is just a power function. However, once I square everything and throw it in, this looks much simpler than this does, okay? So if I was to add this together, I would have to basically turn this into square root 2 over 3 over square root 2 over 3. That way I can combine like terms. Then it's going to get kind of messy here. Okay, I'll probably have to do some kind of crazy substitution. Here, however, I can just multiply stuff out and probably just use the u substitution after I simplify everything. Okay, if not, there is a root here, so I might have to use some sort of a trig sub. Okay, so it should be clear here that 1 or I is the easier choice for us to integrate. Okay, so my integral from 5 to 8, square root of 1 plus 9/4 y minus 4. So let's go ahead and distribute this 9 over 4 across. So this will be a 9 over 4y. Here, the 4's will cancel, and I'll have just minus 9 plus this 1 will give me a negative 8. From here, let's go ahead and just pull out this fractional part, this 1/4, um, so that we can pull it to the outside so that we have whole numbers. So if I pull out a 1/4, this is 9y. Pulling out a 1/4 from this means I multiply it times 4, so you can check just by multiplying this back. So the square root of this is 1/2. Okay. And so now we have the square root 9y minus 3/2. Let's go ahead and make a u substitution and we'll differentiate both sides. So du will be 9 dy. Okay. And then we really want to isolate dy because you could see we don't have a 9 times anything over here. So we'll divide both sides by 1/9. So when we make this substitution, this will be a u to the 1/2. This 1/2 and this 1/9 is a 1 over 18. Our power here is going to go up to 3/2, and we'll multiply it by the reciprocal of that. Okay, so we have 1/18, 2/3. The 2 and the 18 can cancel. This will turn into 1 over 9. Right? We'll go ahead and resubstitute my u value for my 9y minus 32 and plug in our 8 and our 5 at the same time. So now we'll just start to simplify some more. This turns into 40. This turns into 13, right? So we basically have 45 minus 32, and this is 72 minus 32. Okay. So this is 40 cubed square root, 13 cubed square root. So we can pull out one full 40 and one full 13. And then we can simplify, at least for this 40. Um, so just to show you what this looks like, right? 40 is 8 times 5, right? So 8 cubed is actually a perfect group. So I can pull out a full 8. I can pull out a 5. Now on this side, I can pull out a 13. And since it was a cubed root, there's one of each of these left over. Okay. Now 8 itself is 2 cubed. So I can actually pull out um, another 2 here. And then I'm left over 2 that was here. So this actually gets to turn into 80 root 10 minus 13 root 13. Okay. And from here, there's really nothing else that we can do to simplify this. This is 9 and 3. That has nothing to do with 80 or 13. So this is the best that we can get here. So for an example, let's say that the arc length function for the curve, let's find the arc length function for the curve y equals 2x to the 3/2 with a starting point of p naught 1, 2. Okay, so here we're finding the function. So we're coming back to what I described here, where we can find a formula for arc length of a curve, no matter what endpoint we want. Okay, so that's basically what we're doing here. Is that's why we don't have a second point, because we're just saying if we have this function starting from here, what is the length of the curve at any ending point? Okay. So we'll find the derivative here. When we multiply this down and reduce by a power, we get 3x to the 1/2. If I square this, I get 9 and just an x. So we're going to plug this 9x in as a t, because my change of variable here will be an x. So I have the square root of 1 plus 9t with respect to t. Okay. Let's go ahead and use the u sub for this, 1 plus 9t. So we have du is 9 dt. We'll divide both sides by 9. Okay. So when we throw in our substitution, I got u to the 1/2, 1 over 9. So this looks very similar to what I had previously. I have 2 over 2 over 7 from the multiple from this 2/3 that I would have when I do the reciprocal of the 3/2. So I'm going from x to 1. So let's go ahead and resubstitute 1 plus 9t and evaluate from x and 1 and subtract those two values. So I have 1 plus 9x to the 3/2 minus 1 plus 9 times 1, which is 10 to the 3/2. Then we can do the same sort of expansions we were doing before. So this is a 10 cubed, so I get to pull out a 10 squared as a 10. There's still one left over. Here, I don't really have any work for me to do to simplify this. And so that is my final answer here. Okay. This is now a function. So if I want to say, okay, what happens when I get to x equals 7? I would plug in 7, and it'll give me the length of the curve up to that x value. Okay, starting from point 1, 2. You might be saying, well, what about the 2? Well, if I plug in 1 into my function, I would get out 2. So I'm just telling you what the point is, but I don't actually use the 1 and 2 anywhere except for the x value for the bounds of my integral. So let's look at another example. So I'll fix in here and I'll put a header for another example. Let's say that we have a hawk flying at 15 meters per second at an altitude of 180 meters that accidentally drops its prey. Um, since the hawk is flying, uh, the prey is going to fall with a parabolic trajectory. So it's going to fall in an arc. Okay. We can model that arc with y equals 180 minus 1 over 45 x squared until it hits the ground. Okay. So y is the height above ground, and x is the horizontal distance traveled in meters from when the hawk dropped its prey. So we want to calculate the distance traveled by the prey from the time it dropped until it hits the ground. So we want to express our answers correct to the nearest tenth of a meter. The prey hits the ground when the output here is 0. Okay. So we can find x values for this that correspond to an output of 0. So we would just solve for x squared. So we will add 180, multiply both sides by um, a negative 45. So that gives us a positive 180 times 45, square root the x squared, so square root both sides, and we get 90. We don't need plus or minus because we're only moving in one direction here, okay? So 90 meters from where the prey was dropped is where it hits the ground, okay? So that's a horizontal distance. We're not calculating the horizontal distance. We're calculating the distance that it traveled, right? So horizontally, yeah, it traveled 90 meters. But what we want to know is the actual distance traveled completely. So we're going to find the length of the curve that it took, right? So I'm going to take my y function, I'm going to find its derivative, and then I have to square it, right? So I'm going to have this 4 over 2025 x squared. I'm going to add that to 1 and take the square root from 0 to 90, okay, because it's dropped at x equals 0, and it travels until it hits the ground, which is 90 meters away. So we can make a substitution here, okay? So since we have an x squared term under this, it doesn't make sense to make a u sub. We would use a trig sub. And so we would go back to our trig sub section and say, okay, what kind of form does this have? It has the same form of our tan function. So we're going to use the substitution, x equals 45 over 2 tan theta. That way when I square this, these things will cancel, and I'll end up with the 1 plus tan squared, and then I can substitute in my secant squared, right? So once I throw everything in here, okay, I got the integral from 0 to 90 of 1 plus 4 over 2025. This will end up being the reciprocal of this and end up canceling out. I'll get my tan squared, and I can substitute everything in. So this dx right here, I'm just waiting for later. I'm just going to kind of focus on one thing at a time since it's been a while since we've done one of these, most likely. So we'll go a little bit slower. I know this 1 plus tan squared theta is secant theta. Okay, I can substitute my dx for that sine secant squared theta d theta and the 45 over 2. And since now that everything's in theta, I'll go ahead and specify that these are x's, right? Just to keep everything clear here. We know that this is secant squared, square rooted is just secant. So this is really secant cubed. It's probably a good idea to keep them separated so that we can do integration by parts. So one I will differentiate, the other I will integrate. So derivative of secant is secant tan theta. The integral of secant squared is tan theta. So I can go ahead and just form my secondary integration by parts through this. Oops. And so I got the 45 over 2 on the outside, this um, positive secant times tangent, okay, which I'll evaluate from 0 to 90. And I'll subtract from that the integral from 0 to 90, second theta, tan theta times tan theta. So we get the tan squared theta, second theta. Okay. So the reason we stop here instead of continuing to go, it's just going to get very convoluted in here. There might be some things I can do to make this a little bit easier to work with, right? Such as the secondary option, when we have powers of tangents and secants, I can do my other trig integration. So I'll substitute the secant squared minus 1 for the tan squared. Um, and then I can go ahead and save one secant squared for this. Okay. All right, so I have the first part. So I'm saying that's equal to, so just to remind us what we have. So I have this part that I'm going to integrate from 0 to 90, or evaluate, I'm sorry. And I'm going to substitute this secant theta times secant squared theta, and this secant theta. So if you notice here, this is nice because I have one of these already. Okay, so I can just subtract this one out to this one, which is, I'm sorry, add it together, okay, since it's negative. And here, it was a minus 1, but it's being subtracted, so it's just a secant. So here, again, note that 45 over 2, integral from x is 0 to 90, secant cubed to secant squared theta, is the right-hand side of my original integral, not the left. Okay, my original integral that I'm trying to find, just so that we're clear, is this thing. Okay, so this was a right-hand sided portion, right? It's not equal to what I was trying to find before. So the reason for that is that when I kind of add this to the other side and I get an equality of this, I get just 45, right? So I have this 45 over, I'm sorry, this 2 will cancel, right? So 2 of these is going to be equal to what's left, which is this 45 over 2 secant theta tan theta, evaluated from 0 to 90, and then that secant that's left over, okay, right here. So this 45 over 2 is the same as 45 over 4 over secant theta plus 45 over 4, right? So if I were to um, have just 45, it would be equal to what I have, but since I have 45 over 2, I would divide the whole thing by 2, okay, if that makes sense here. So that is why this 45 over 4 and this 45 over 4 here is what's left, okay? Because what I have in the middle is this 45 over 2 for the secant theta, secant squared theta. So my length is going to be this 45 over 4 secant theta tan theta from 0 to 9. And then if I integrate secant theta, you get natural log secant theta tan theta. Okay. So again, if you are confused, I made an equality for this, okay, because this is what I had. Okay, this 45 over 2. If I distribute it over to, sorry, here, okay, secant cubed on the left side, I expanded this to the secant theta tan theta 45 over 2 and this tan squared theta secant theta 45 over 2. Okay, so this part is equal to this thing, but it is still on the right hand side of my equation. Okay, so then when I came down, I can just say this part is equal to this part, right? Because it is. If I move up in line. So then when I get here, I'm not saying this is my left hand side. I was just saying this was a previous value of my right hand side. Okay, and so if I come back down as I'm saying this is equal to this, which is equal to this, which is equal to this part here ends up having another secant theta secant squared theta. Okay, and so I'm just informally setting them equal to each other because they are equal. This is just what I had higher up the line, and then this is what I have lower down the line. So I'm going to move this to the outside by adding it to both sides. and getting the 45 of this is equal to this, okay? But I don't have 45, I have 45 over 2. So everything that I have left over needs to be divided by 2, okay? So in order to have everything actually equal, I just kind of went back and made some equations that I had, okay? So this is what's left. I have 45 over 4. Secant of theta is the natural log of the absolute value of secant theta plus tan theta. So now I'm ready to evaluate everything from 90 to 0. If I come back to my original x, which is 45 over 2 tan theta, um, I can now start to isolate theta. So I will divide both sides by not tan theta, okay? And that tells me what my triangle will look like, okay? My triangle here, the tangent is 2x over 45. Basically, this is the denominator, and this is the opposite, okay? So opposite over adjacent. So if I needed to find this, I would, but this is all tangents and secants, so I don't necessarily need the hypotenuse just yet. So my secant then is 45 squared plus 4x squared, right? So me square this, take the square root, and then divide that by the opposite because, let's see, this hypotenuse is 45 squared plus 2x being squared, square rooted. So that's the hypotenuse. Remember, secant squared is the hypotenuse over the adjacent, right? It's the flip, it's the reciprocal of cosine. So I have the hypotenuse over the adjacent, and we'll just go ahead and start to simplify that, okay? So for my integral, right, throwing everything back in there here, 45 over 4, I'll throw in my secant, which is that hypotenuse over 45, and then my tangent, right? So here we're just throwing everything together. 45 over 4, this is the uh, secant, and then this is the tangent, okay? That's the first part. Plus, now I have my secant, or 45 over 4 times the natural log of secant plus tangent, and all of this is evaluated from the same bounds, 90 and 0. So when I evaluate this at 90, notice that this 45 over 5 cancels. When I get 90, I'll get 45 over 5 and a 2 left over on top, so that 2 will cancel with this 2. So what I'm left with is the square root part, with the 45 squared or 90 squared. Here on this last part, we don't get anything crazy like that. I just have one x value here. So I throw in the 90 to that one. And then here I will subtract what happens when I plug in 0. So here, doesn't even matter what's happening here. There's an x multiplied times everything. So when I throw in 0, there's nothing. Here I have a 45 over 4 uh, natural log. And then when I plug in 0, this part goes away. And this turns into just square root 45 squared over 5. Sorry, 45 squared over 45, so that's 45 over 5 or 1. So I get natural log 1 here, okay? And so that's how I get. This 4 comes from me plugging in the 90, right? 45 over 5 is cancels, and then there's a 2 left over, so this absolute value goes with this natural log here, okay? So now let's start to break down what happens inside of the square root. Okay, as we saw before, 90 is 45 times 2. Why do I keep doing that? Because there's a bunch of 45s everywhere. So it's easier to look at 90 in terms of its components, 45 and 2. So here I'll have 45 squared, 4, and then this whole term is squared. And then I'm just doing the exact same thing here. We know that natural log of 1 is 0, so this whole subtracted piece goes away. So all I'm working with now is this square root and this natural log. Okay, so really we'll just start off with the simplifications here. When I do this, I get 45 squared and a 4 squared when I distribute that. Okay. I'm sorry, a 2 squared. 2 squared is 4. 4 times 4 is 4 squared. That 45, it pulled out as a common factor with the 1 here and 4 times 4. Okay. Same thing happens here. There's nothing else that I do here except for the same thing on both uh, square roots. So this turns into 16 plus 1. 45 squared being square rooted is just 45. So this turns into 45 on the outside, 17 on the inside. Same thing here, 45 on the outside, which cancels with this 1 over 45. And all I'm left with inside is root 17. Okay. And so from here, there's really nothing left for me to do. However, so this is the exact answer, right? However, for our problem, if we go way up here, it's asked to express an answer correct to the nearest tenth of a meter. Okay, so could I have just done this in a calculator? Probably, right? But then you guys want to see how to work some more intricate problems, right? So here, approximate value is 209.1053. It said to the tenth of a meter, so I really just need the 209.1. And that is how far the prey traveled total, right? So horizontally, 90 meters. But with the arc included, the full flight path was 209.1 meters, right? So that's significantly more than just the horizontal displacement, right? And that is how we do arc length.